Hello, my name is Andres, and in this video I'm presenting the paper The Complexity of Approximating the Complex Valued Potts Model for the conference Mathematical Foundations of Computer Science. My co-authors are Andres Galanis and Leslie Goldberg, both professors at the University of Oxford, where I'm doing my PhD. In this paper we study the Potts model from a computational complexity point of view. So first, maybe let me introduce this model. The Potts model has two parameters, a, a positive integer q and a complex number y that is known as the edge interaction of the model. We also have a graph G, and we define configurations over this graph as the q colorings of the graph. Okay. Now the Potts model gives a probability distribution over these configurations, and the probability of a configuration is proportional to the following quantity: the edge interaction to the number of monochromatic edges under the Q coloring. Okay. The normalizing factor that makes this probability distribution is known as the partition function of the Potts model. Um, so you can see the formula on the screen. It's obviously a sum of the Q colorings of the graph. Maybe let's go quickly through this example. Here we have a graph with three vertices, and we want to compute the partition function of the Potts model for this graph. Really there are three type of Q colorings here. Those that assign the same color to every vertex, and thus they have three monochromatic edges and contribute y cube to the partition function. Those that all, only assign the same color to two vertices, and therefore they only contribute y to the partition function. And lastly, those that assign different colors to each vertex, okay, and only contribute one to the partition function. So by adding the Q colorings of all those kinds, we obtain the partition function of the Potts model for this graph. So now the problem of evaluating this partition function at two fixed parameters has been studied, and it turns out that this problem is number pH, except when the edge interaction is 0, or the pair QY is one of the 7 special points where evaluation can be performed in polynomial time. Okay. Interestingly, when Q equals 2, the edge interaction is larger than 1, which is actually the case of the ferromagnetic Ising model. This partition function admits a fully polynomial time randomized approximation scheme. And this is a famous algorithm of Jerome and Sinclair. So we have an example of a problem whose exact version is number pH, but the approximate version is easy. So now the question is, what happens to other pairs of parameters? Some work has been done on that, and in the next two slides I'm going to go through that work. First, focusing on the case of the Ising model, the case Q equals 2. So here we have 5 easy points, 0, 1, minus 1, I, and minus I. We have the f-prime of Jerome Sinclair that we mentioned before. When the edge interaction is smaller than minus 1, the problem is equivalent to approximately counting perfect matchings. Everywhere else, Goldberg and Wu prove that the problem is NP-HA and sometimes number pH. Now, when Q is at least 3, actually nothing is known for non-real edge interactions. The real line has been studied, so we know 0 is an easy point, and when the edge interaction is at least 1, the problem is equivalent to approximately counting independent sets in bipartite graphs. Everywhere else on the real line, the problem is NP-HA, and actually one can show number p-hardness when the edge interaction is between 1 minus q and 0. In this case, I'm plotting only the case q equals 3, so this 1 minus q becomes minus 2, but the picture would be uh, essentially the same one for larger values of Q. Now, so in this paper we study these approximation problems for non-real edge interactions. We want to fill in the previous plot, okay? But why are we interested in non-real edge interactions? There are a few reasons for that. First, to begin with, physicists always work with complex edge interactions because actually phase transitions uh, occur precisely at the real limit point of complex zeros, okay? Maybe a more recent motivation is that the best known approximation algorithms on bounded degree come from understanding zero-free regions in the complex plane. So one has to study complex edge interactions uh, of for this matter. Finally, there are some connections with quantum computation, but I'll come back to those later in the talk. So in the rest of the talk, first I'm going to formally define the computational problems that we consider. Then I'm going to state our main results. And finally, I'll give some of the ideas that you can find in our proofs. So for the computational problems, we fix the two parameters, q and y. So q is an integer that is at least 2. For y, we restrict ourselves to algebraic numbers because we know how to compute with them efficiently. And now we distinguish two approximation problems. The first one is the problem of multiplicatively approximating the norm of the partition function. And the multiplicative error here is a constant k. But really, this is equivalent to giving an f-prime for this quantity by an easy powering argument that you can find in our paper or in previous papers on the matter. And the second problem, the second approximation problem, is that of giving an additive approximation of an argument. It could be any argument. It doesn't have to be the principal argument of the partition function at the pair qy. Okay, now I can state our main results. So in this paper we give a complete classification of the complexity of these approximation problems for non-real edge interactions. Our main result in that regard is theorem 1 that deals with the case q at least 3. So when the edge interaction is non-real, we show that these approximation problems are non-BPH, except in two cases, when q is 3 and the edge interaction is a root of unity of order 3. Actually, hardness is maintained when the input graph is promised to be planar, which will prove to be useful in the connections with quantum computation. Now, the result is optimal in the following sense. The two exceptions found in the statement are actually two of the easy points for the Potts model, where evaluation can be performed in polynomial time. When q equals 2 and the graphs are planar, the partition function can be computed exactly in polynomial time. Therefore, the statement as it is cannot be extended to planar to q equals 2. But we will come back to that case later. So the plot that I showed before for q equals 3 is now, with the help of theorem 1, will become now this one. So now we know hardness almost everywhere. And the plot would be essentially the same one for larger values of q. And we also have another result, theorem 2, that deals with the complexity at the segment minus 1 minus q and 0. So what this result says is that the approximation problems on this segment are hard even for planar graphs, okay? Which was open, that was an open problem for q equals 3 and 4. But anyway, moving on to the case of the Ising model, when q equals 2, uh, we also give a result for this case, and we show that the approximation problems are NumPH, except when the edge interaction is I or minus I, which again are two of the easy points of the POTS model. So now the previous picture where we had only NumPy harness at some segments or lines or curves of the complex plane uh, becomes this one. Now we have NumPy harness almost everywhere too, and we fully understand the complexity of these approximation problems. We also have a more general version of these results for TAT polynomials. So, but first let me introduce these polynomials. The TAT polynomial of a graph G is the sum over all the subsets of edges of the graph of the following monomials. Q to the number of connected components in the graph with the same vertices as G and the edges of A, okay? Times gamma to the size of A. I should say here that Q and gamma are complex numbers, but when Q is a positive integer, actually the partition function of the POTS model is really this polynomial with the change of variables gamma equals y minus 1, okay? So the TAT polynomial generalizes the POTS model. Actually, for us, it's more convenient to work with TAT polynomials. So that's what we do in most of our results under the assumption that Q is at least 2, that obviously includes the POTS model. Now I can state theorem 4. Here Q is larger than 2. And what we conclude is that for non-real gamma, the approximation problems for the TAT polynomial are number pH, except when again Q is 3 and gamma plus 1 is a root of unity for the 3. That was the exceptions found before for the POTS model. And here hardness is also maintained when the input graph is promised to be planar. So obviously we obtain theorem 1 as a particular case of theorem 4 by setting Q to be an integer here, okay? But the thing I want to expand on here is the connection with quantum computation. So first, a bit of background. It turns out that polynomial time quantum computation can be simulated with the help of an oracle for loose approximations of the Jones polynomial at the fifth root of unity. I don't want to get into details and definitions here, so I will refer to the paper of Boderwich, Friedman, Lovaas, and Welch, or our paper for that. But the thing is, the Jones polynomial of a link is actually a TAT polynomial of a planar graph. And for this reason, the authors of the previous paper posed the following question. What's the complexity of determining the sign of the real part of the TAT polynomial of a planar graph at the fifth root of unity? Well, the reason for posing this question is that with an oracle for this problem, they can obtain approximations, these loose approximations for the Jones polynomial, and therefore simulate polynomial time quantum computation. What we prove is that this problem is number pH, actually, just answering their question. So now, in the next 10 minutes, I'm going to give some of the ideas that you can find in our proofs. First, I need some preliminary material. So here we have the random cluster definition of the TAT polynomial that we saw before. There is another definition known as the XY parameterization of the TAT polynomial. This is really a change of variables, and it will be useful later on. That's why I'm including it here. So the change of variables is y is gamma plus 1, so y is as it was before for the POTS model, and we choose x such that x minus 1 times y minus 1 is cubed. So basically xy is in this set HQ are defined on the slides. And now let me ask the following question. So as here we have harness at some point x2, y2 using this notation, okay? Actually, later in this talk, y2 is going to be a number between -1 and 0. And now we want to translate harness from this point to another point, x1, y1, that could possibly involve non-real numbers, okay? Can we do that? The answer is yes, there is a tool in the literature to do that, and this tool are shifts, okay? So I'm going to give overall idea of the definition of shift. For the precise definition, I'll refer to our paper. So a graph first a graph implements a point using another point with terminals st. If the graph, when all the edge interactions are gamma 1 or y1, sorry, behaves as really as an edge with edge interaction y2. Okay, so what I mean by behaves is that, so if we look at the two graphs that you can see on this slide, the partition function evaluated on the graph uh, at the left is really the same one as the partition function of the graph at the right, up to a constant factor that is easy to compute. So if we know how to evaluate the TAT polynomial at x1, y1, we know how to evaluate the TAT polynomial at x2, y2. Therefore, if we have harness at x2, y2, we have harness at x1, y1. That's the idea, okay? Now we say that there is a shift from the first point to the second one if there is a graph that using the first point implements the other one. So now that we have this notation, actually the issue here is that shifts give limited harness results. The reason for that is that we cannot expect to be able to give a shift from any point with non-real numbers to some fixed points where we know harness, okay? So in order to solve that, we define a generalization of shifts, and the idea here is implementing approximations of fixed edge interactions, okay? So this generalization is called polynomial time approximate shifts, and they are algorithms that for any positive integer n compute in polynomial time in n a graph G that using the first point implements a very good approximation of the second point. With very good, I mean that the additive error that we make is at most 2 to the minus n, okay? These kind of approximations have appeared in the work of Goldberg and Jerome before for real algebraic numbers, but what we prove in this paper is that we have a polynomial time approximate shift from a point to another one, then the approximation problems on the second point reduce to the approximation problems on the first point, okay? So if we have harness on the second point, we can translate that to the first point. Actually, we work with a particular kind of these approximate shifts known as series parallel, or well, we define them as series parallel. Here, the graphs have to be series parallel by definition. We also define polynomial time approximate theta shifts as those when the graphs are theta graphs. I I don't have time to go to give definitions of these two type of graphs, but maybe what I want to highlight is that these graphs are always planar. So with these approximate shifts, we preserve planarity in our reductions, and as we said before, we're interested in making our results true also in the planar case. And actually, with this type of approximate shifts, we can prove a transitivity result that will be useful in our proofs, okay? So now I can state the main technical result of our work, theorem 5. Here Q is at least 2. What it says is that for any two pairs of algebraic numbers x, y, and x prime, y prime, such that y prime is between -1 and 1, there is a polynomial time approximate series parallel shift from the first pair to the second one. Except in a few cases, and these cases really are those where we didn't get number p hardness in our main results. So what I'm trying to say is that this result is what essentially determines if a point is hard or not for non-real edge interactions. Now combining this result with lemma 8, if we have hardness at some point between with edge interaction between -1 and 1, then for that value of q we would obtain hardness for any y as in theorem 5. Okay, and this is what we apply to prove our main results. Now let me uh, give some insight on the proof of theorem 5. There are three steps here. The first step is giving a approximate theta shift from the original point to a new point, such that this new point has edge interaction between 0 and 1. Now using this new point, we give a polynomial time approximate theta shift to the point we are interested in, and now we merge both approximate shifts using this transitivity result that we mentioned before. There are a few challenges here in making this work. First, the thing is with step 1, which is actually takes most of our work. The thing is the new point that we find, these numbers might not be algebraic. Okay, what we know is that they are polynomial time computable. That is, we can efficiently approximate these numbers by rational numbers. So in the next steps of the proof, we have to work with polynomial time computable numbers. The second step actually was carried out for algebraic numbers, real algebraic numbers only, by Goldberg and Jerome. But we need to extend the results to polynomial time computable numbers, and then we have to prove this transitivity result, which is actually not true in general. So we will need a few assumptions here that we have to verify. So finally, once we have theorem 5, the only remaining thing to do is showing hardness at some point between -1 and 0. Luckily for us, that had been done before by Goldberg and Jerome. They reduced counting minimum cardinality STCAT to approximating the TAT polynomial. And the reduction is essentially a binary search using implementations to tune some of the numbers there, and this way they compute the solution of this counting problem. However, the thing is that this counting problem is not hard for planar graphs, so they only show hardness for arbitrary graphs. Now, because we want our hardness result to hold for planar graphs too, we have to do a bit more work. Our contribution here is reducing exact evaluation to approximate evaluation of the TAT polynomial, which I find quite interesting. And the thing is, exact evaluation on planar graphs is known to be number pH. Now, there are a few challenges on this approach. First, we have to reduce the computation of the TAT polynomial to the computation of some ratios of partition functions. Then, to compute these ratios, we need very good sharp lower bounds on the knob of the partition function, but luckily for us that have been studied by number theorists before. And we also need to compute the representation of an algebraic number from a good approximation of this algebraic number, but for that we can use the lattice basis reduction algorithm of Cannon, Lenstra, and Novas. So combining all this, we can obtain this new reduction and prove our results. Okay, so that's all I had for this video. Thank you for watching it, and if you have any questions, feel free to send me an email. I'll be very happy to get in contact with you.